All right, welcome to the second lecture for analytical chemistry. Today, let's see how long it'll be. I feel it'll be a little bit shorter than the first one. We will be essentially talking about uncertainty in measurements, how to perform some mathematics on those uncertainties, and then I think I want to start talking about calibration curves with you. That'll probably be what I end up leaving off with today. So let's start with talking about uncertainty in measurements. Certainty. Now, there are two types of uncertainties: absolute and relative. It's usually percent relative. So you have definitely seen these before, either on pieces of glassware in the chemistry lab, randomly throughout your life and things. You've definitely seen this measurements before, and what they are is essentially this plus or minus some number. This uncertainty is will be given to you on the instrument. Some of the instruments do indeed have the uncertainty on them, but other instruments may not have the uncertainty on them, and you could calculate the uncertainty technically with I'll show you how to do it in a moment or two, but it's very, 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 very straightforward. So another sort of word for another word that maybe make more sense to you in uncertainty also is tolerance. You see this word more so in machining and mechanical processes and such more so than in chemistry and in math. And essentially, you could think about. I think thinking about it as tolerance might be simpler. You could think of perhaps you have a hole and you have a bolt, and that bolt you want to fit inside that. So let me outline. You want to fit this bolt in this hole. And the tolerance essentially is the level of wiggle room between the outer edge of the bolt and essentially the inner edge of this hole. So when you could think about it as that, as you increase the tolerance as on something, you decrease the amount of wiggle room that's available. And if you increase the tolerance, or rather, if you decrease the tolerance, you increase the amount of wiggle room, and if you increase the tolerance, you decrease the wiggle room. So when you think about it in terms of uncertainties, as that plus or minus symbol gets bigger or smaller, you're actually just increasing or decreasing the wiggle room between the actual value and the value that you are measuring. So let's say you measured 43.2 milliliters. You measured that, but let's say that the instrument's uncertainty was plus or minus 0.3 milliliters. What does this mean? That means that you did not actually measure 43.2. You can't say that with utmost certainty. What you actually measured is some value that is plus 0.03, so 43 reset. So 43.2 plus 0.3, and let's say 43.2 minus. This gives us 3, 4, 5. 5. Take away 3. This gives us 42.9. So what this plus or minus says is, although we measured this value right here, our actual value exists 43, or is this between 42.9 and 43.5. And now you can sort of see is, as we make this number smaller and smaller, we're sort of narrowing the space of what this, or how big this line essentially is right here. So by decreasing the uncertainty or the tolerance, or rather increasing the tolerance, and decreasing the uncertainty, we are shrinking that space of possible results that our measured value could be. So usually we want very low uncertainties, and that's why we use different instruments to measure different things. And you'll see that specific pieces of glassware, for instance, have specific uncertainties tied to them. And usually, if you're measuring very small quantities, you want a very small uncertainty associated with that value. So if you did repeated measurements, you would have very little variation throughout the measurement. Because although even if you measure things absolutely perfectly every single time, there's no guarantee that you will actually measure this 43.2. Your value will always exist between this 42.9 and this 43.5, regardless of how many times you hit this 43.2. And it could exist in multiple places throughout this, in between these two numbers. And this is essentially where that this variation and jiggle comes from. If you recall to when I said when you created those graphs for the first experiment, you sort of wanted your results to bounce up and down from between the average mark. And that's essentially because your values are controlled to a point up until this uncertainty comes into play. You can only measure things so exactly until the values start to exist in this random gray area. And the idea is you're trying to take this random gray area and decrease it to as small of a quantity as possible. So that's the idea here when we are talking about uncertainties with these plus or minuses of these values. So let's see. How should I read? So what you could say is, it is equivalent to what you measure versus where actual value lies. So here is something that actually is not, well, essentially what I'm just putting into words right here, but probably overly explained for the last few moments. But this is essentially what's going on and what we're going to be mainly talking about today. But I want to point out this one more thing, and we have something known as digital devices. And we have analog devices. Now, the way we essentially will record the uncertainty of an instrument, one, if the device states their uncertainty on it somewhere, you're done. You already know the uncertainty of the device. You know that's its uncertainty. However, if the device does not state its uncertainty, this is the general trend we will use to determine it. And it's not usually stated, but there is a difference between the way we do it on a digital device and the way we do it on an analog device. And there's a pretty interesting reason for that. It's a pretty good reason. Digital devices measure things in ones and zeros. And analog devices essentially are measuring things on this continuous wave of different values. So pretty much you could think of an analog device as measuring something as this smooth waveform, while a digital device is constructing waves that are to the best representation of this smooth waveform. So this is actually exactly how music works. As we increase in music, actually, the bit rate of the audio, or the amount of data that is being analyzed every second, we could pretty much put more and more values in this same bit of space. And as a result, this wave that looks very linear here could become more smooth in idea or in appearance. However, if you ever zoomed into it, you're not getting a smooth. You can think of it sort of like a pixel approach in a way. It's not smooth and continuous like that of a analog device. An analog device is essentially giving you exactly what is being represented in nature. You're getting an actual representation of what's going on with an analog device. You're getting movement in the actual world, where in the digital device you have to do some sort of transcoding where we bring these analog values into a series of ones and zeros. And these ones and zeros are approximations of the actual value. And the more amount of data points you collect, the better that approximation will be. But you'll never actually be able to reach an absolute point where the digital device is able to 100% perfectly capture the analog device. But that's totally okay. It doesn't matter, because that excess data is not important to us. It's just not important to us. For instance, with audio, the human ear is only able to hear to a certain level of frequencies. As we increase the rate in an audio track that's on a digital piece and an analog piece, for instance, we get to a point where even though the analog piece is giving us a smoother signal, we're not able to discern the difference between the signals, so all that excess is useless. And this is, in a way, this is how digital devices shine in the aspect of data loss. A lot of these cables that you'll get that send signal through from one place to another, that send signal digitally, a lot of these devices that have all this excess shielding, or that's overpriced and they try to offer you a better product, it's mostly a lie. Because when you're sending a digital signal, you literally get a 0 or a 1. You don't get a range of values in between. So it's not like if you increase the clarity of the signal, you're seeing the 0 a little bit better than you were seeing it before. No, the device doesn't care how dirty or clean that 0 or 1 comes through. It reads as a 0 or 1, or it just doesn't read at all. Those are the only two cases for a digital signal. With an analog signal, this excess shielding does have a purpose, and it is necessary. because when you're sending data through a device in an analog fashion, you're sending it in this wave-like function. It's usually a sinusoidal curve. And as a result, if you have any sort of influence on this curve, it could be essentially changed in some sort of way. You could drastically influence the signal. So analog devices are significantly more susceptible to outside noise than digital devices. And in that same regard, analog devices have a different level of uncertainty as digital devices. And it sort of comes from that idea of we have zeros and ones in digital. So digital devices uncertainty, if it's not stated anywhere on it, will always be plus or minus the smallest division. And so what do I mean by that? Let's say we have a scale like the ones in our labs. Let's see. We have 0.1, 2, 3, 4. We have 4 digits on this scale. That means that this last digit is our smallest decimal place. And what's the smallest value this last digit could be? Well, this last digit's smallest value is 1. So the uncertainty on all of our scales at the school are plus, or at least the ones, the analytical balances, that is, are plus or minus 0.000. So this is our analytical balance uncertainty that is associated with. Essentially, let's say we had a device that was 0.00. The uncertainty that would be associated with that would be plus or minus 0.0. There we go. Now, the uncertainty associated with an analog device is slightly different. It is plus or minus the smallest division all over, or divided by 2. So what do I mean by that? Let's say we had a thermometer. I have a picture. A ruler here. I would prefer a volumetric device, but suitable. Let's change our color to black. Let's say this is centimeters. Say we want to zoom in. Ready? And we could see that I don't want that. Right around there, I think you'd agree with me. So, if we use the definitions that I just set up, this is the centimeter. This is a centimeter ruler. That would mean that this is 1 centimeter, 2 centimeter, 3 centimeter, and that would mean this is essentially point something centimeters. So the smallest unit, so the smallest division on this ruler would be 0.1 centimeters. Because that is essentially what the smallest division is. And let's say we wanted to treat this as millimeters. We know that the smallest, if we go from centimeters to millimeters, the smallest division would be 1 millimeter. Now, based on all of this, we could use this, this formula that I set up right here, where we essentially, because this is an analog device, we know we're going to take the smallest division and divide it by 2. Back to this. And let's say we have 0.1 centimeters. We're going to divide it by 2. And we have 1 millimeter. And we're also going to divide it by 2. We get 0.05 centimeters, and we get 0.5 millimeters. We're essentially taking this 1, cutting it in half, so we're getting 0.5. We're taking this 0.1, we're cutting it in half, we're getting 0.05. This would mean that the uncertainty associated with these instruments would be plus or minus 0.05 centimeters and 0.5 millimeters. So here we have the uncertainty associated with this centimeter ruler that I pulled up here. Now let's actually look at this device. We see that this the square that I drew, it starts at our 0 mark. We measure it all the way up to here. We see that it is at least 4 centimeters on our marker, and that would mean that that is at least 40 millimeters. We see that we get to that 0.5 point, so it is 4.5 or 45, 4.6, 46, 4.7, 47, 4.8, 48. So we know at this point we are at least 4.8 centimeters or 48 millimeters. So let's write that down. So 4.8 or 4. So at this point, we're not done. Remember, when we ever record any measurement on on any sort of device, we always want to make a guess about that last digit. At this point, we know it's 48. We know for a fact it's 48, and we know that for a fact that it's 4.8 associated. We know 100% it's one of those two values, or it is definitely one of those values. But we need to make a guess to bring this one step further. So let's put a point right there. We see that it's coming somewhere between the 48 and the 49, or the 4.8 and the 4. I would actually say it's near smack dab in the center. So let me maybe a little to the right. Let's use 6. So this would be the value that I pull up here. So I guess this last value of 6, I guess this last value of 6, and here we pull this last value of 6 into these two measurements. This would be millimeters, centimeters, and what we would then do if we wanted to more accurately report our measurement, we would add that uncertainty associated with plus or minus, plus or minus. So if it's centimeters, it's 0.05 centimeters. And if it's millimeters, it's 0.5 millimeters. So what this says is, well, our actual value, let me actually here. This says that our actual value exists between, let's use just the millimeters. I'm not going to use the centimeters, just the millimeters. So let's say that says that our actual value is between 48 this 6 minus 5 is 1, 2, 49 point, well, so this right here is the range of values that our actual value exists between. For 100% certainty, we know it's between 48.1 and 49.1. We don't know where, but we know it exists between those two numbers based on the uncertainty of this measuring device that we essentially have here. This gives us the final rule of significant figures that I want to talk about, and this is what you could actually consider to be the true ruling of significant figures. And what this rule states is the first digit of absolute uncertainty is the last significant digit in the answer. And so what do I mean by that? Let's say we had the number 0.54321 and the uncertainty associated with it is 0.0002. We see that this is in the 1, 2, 3, 4. 1, 2, 3, 4. That would mean that this digit right here is the last uncertain digit, or the last significant digit in the answer. So the first digit of absolute uncertainty, so that's this one. First digit absolute certainty is the last sig fig. And so we could rewrite this as we would want to rewrite this as 0.5432 plus or minus 0.000. This is how we go about doing this. And it's sort of interesting because the uncertainty associated with any number will always tell us essentially the last significant figure that we should have in our answer. This rule goes above all other significant figure rules, regardless. This will always give us the correct answer, period. Let's do some more examples. Let's say we had 0.04368, say 43, plus or minus 0.01362. Notice how our uncertainty has 1, 2, 3, 4 digits. Our uncertainty could only have one digit. We only care about that first one. If, for instance, actually do that, we have a 5 there, our uncertainty would become 0.002. Because we're going to round it up. And then we would attach it to this number. 0, 4, 3. 0, 4, 3. Same amount. That's how we attach the uncertainty here. Let's see, what other possibilities can we get? Let's say we have 0 0.157. Let's say it was plus or minus 0.2. We would see that this would be what we would want to round our value to, or the last significant figure would be this one. See that that's a 7. Therefore, this would turn into 0.016 plus or minus 0.00. I think that's all you really need to worry about for at least this part right here. I can't think of any other examples off the top of my head at the moment. That's pretty much it. These are all examples of what are known as absolute uncertainty. The next thing we're going to do is talk about percent relative uncertainty. And this is what this is the absolute uncertainty divided by the actual value it's attached to, multiplied by 100. So how do we go about doing that? Let's say we have 0.034 plus or minus 0.002. This is an absolute form. In order to get the relative form, we simply take 0.002 divided by 0.04 multiplied by 100. We do that really quick. Get 0.02 divided by 0.34 times 1. So that looks like it comes out to around 5.9%. So we will have 0.034 plus or minus 5.9%. Do another one. 0.129 plus or minus 0.001. If this is the absolute and we want to turn it into the relative, we would simply do 0.001 divided by 0.129 multiplied by 100. That be is 0.78. Percent. this would become 0.129 plus or minus technically, that's really all you do. You just take the whatever the plus or minus is and form this division and multiply by 100, and you'll get the percentage. Normally, you will see things associated with an absolute uncertainty. And the reason why I'm not really performing any rounding on these is usually with relative uncertainties, we're using it to plug into a formula, as you'll see in the next example. And instead of using it as it's just being expressed as this, where you usually express things in absolute uncertainty. And when we are ever converting between one form and another, we don't want to introduce rounding errors. So that's mostly the reason why I'm not really rounding any of these relative uncertainties. Let's actually use these relative uncertainties. And this will be the last thing we talk about today, where we are adding, subtracting. Let's say that E equals absolute uncertainty. Let's say that percent %E equals percent rel uncertainty. So when we are adding and subtracting uncertainties, and by that I mean if we have this one, 8, 0.29, 0.48, such. Then we have these following uncertainties associated with them. 0.02, 0.01, 0.03. We would add these first numbers together. So let's say get 2.15 plus or minus. We would not add the uncertainties together. Instead, what we want to do is the following. We will take the radical. We will take our absolute uncertainty squared, add it to the next absolute uncertainty squared, add it to the next absolute uncertainty squared, and so on and so forth. So 1, 2, 3. So we go to infinity essentially. This is for addition and subtraction. So let's actually do this. So when we square values under the radical and add them together, this is typically known as quadrature addition. And so if we do that, we'll get 0.02 squared plus 0.01 squared plus 0.03. We will perform this math. We get 0.037 because we only want the first digit. This comes out to 0.04. And we get 0.04 is our new value. So whenever we do any sort of addition or subtraction, we will do addition and subtraction in the way that we normally do, and then we will essentially do this essentially perform this this math in quadrature for the absolute uncertainties. Remember, we have to use the absolute uncertainties when we are doing quadrature addition for the addition and subtraction of uncertainties. When we perform multiplication and division of uncertainties, we need to do something slightly different. So let's say that we had 0.158, 0.111, and 0, or no, let's not use 0. It's 1.13. Say we had plus or minus, plus or minus, plus or minus. It was 0.002, 0.007, 0.004, and let's say we have multiplication this. So again, we would perform a multiplication exactly as we would, and that gives us 0.0199. So keep 3 sig figs so far. We have 3 sig figs here. And now we are going to perform the mathematics on this section right here. Instead of essentially using the absolute uncertainties, we need to convert each of these absolute uncertainties into relative uncertainties and then plug it into the same exact formula, but we are instead using the percent uncertainties this time. One, two, three, so on and so forth. So this is for multiplication and division. How are we going to do this? First, we calculate all of the relative uncertainties for these values. So we do 0.002 divided by 0.158 multiplied by 100. And we do 0.007 divided by 0.111 multiplied by 100. And we do 0.004 divided by 1.136 times 100. And we get following values. Approximately 1.3% here. Get 6.3% here. And we get 2.9%. Ideally, if you do this calculation, I would keep every single digit possible when you're doing it, so you could introduce the least amount of rounding errors possible, because we're going to use this number now to do another calculation. That's right here. Take this 1.3, square it. It's 6.3, square it. I'm going to take this 2.9 and square it. And when we do that, we get this 7.1%. So this is a new value. It would be 7.1%. But we want our value to be an absolute. So instead of using this relative percent, we need to convert back. So how are we going to do this? Well, we are going to take this 0.0199. And then we are going to multiply it by this percent. But remember, when you're multiplying by a percent, you have to multiply it by its decimal equivalent. So what is 7.1% as a decimal equivalent? And that is 0.071. When we multiply, we get 0.001. So look what happens to our answer. We get 0.0199 plus or minus 0.001. Now, if you remember my the rule that I gave you with significant figures is that the least uncertain, the first actually go back to it. Exactly what it said. Where are you? The first digit of absolute uncertainty is the last significant figure in the answer. So our first digit of absolute uncertainty is here. So this in the 1, 2, 3 points to the right of the decimal, and we see 1, 2, 3. Oh, look at this. This 9 is the last significant figure. So we actually need to change this answer. Although, if we did not have these plus or minuses here, we'd see that we followed our rules for multiplication. This rule says 0.158, 111, 136. We see that our last digit in each of these plus or minuses are indeed associated with the last digit in our actual value. But when we performed our mathematics, we see that lost a digit. We essentially changed our value slightly based on these new rules compared to the old rules of accounting significant figures. So what we're going to need to do is transform this answer from 0.0199 to 0.0. Well, this 9 is going to be rounds up. So this 2 is going to, or this 1 is going to turn into a 2. The 9 is going to become a 0. And then we add this plus minus 0.001, and we're done. This would be our final answer right here. So generally, the idea of what we have talked about today is how we are going to, or rather, where the reason why we come across, or where we have where uncertainties come from, how we play with uncertainties, and by adding, subtracting, and multiplying and dividing them, and how uncertainties actually influence the amount of significance of an answer. So I think this will be all I talk about for today. It'll be, let's see. Next week, we will talk about calibration curves. We will talk about a few more statistical things. And then we'll break into some chemistry stuff. And then we'll probably talk more so about the equipment for the last bit of the class. More so on the technologies like the mass spec, the NMR, the HPLC, the UV-Vis, the IR, and the atomic absorption. I want to try to hit pretty much all the machines. I'm more interested in that than anything else, really. So I will upload an assignment at some point where you guys will be performing mathematics on uncertainties, so expect that. But other than that, you shouldn't have to worry about any other assignments at the moment. Take care, and until next time.